Okay, welcome to the second lecture this week, lecture 6 on numerical analysis of ODEs. So in the first lecture this week we started chapter 2, the explicit one-step methods. So the first numerical methods we're going to study for solving systems of initial value problems or for systems of ODEs. Okay, so we started the section by introducing the simplest one-step method, namely the Euler method, by basically using Taylor expansion. Taylor expansion at the initial point, T naught, where we know both the solution, the function value and the derivative of the function, allows us to do first order Taylor expansion, and then we truncate this first order Taylor expansion, this linear approximation after a short time, a time step, T1, and there we repeat the process again. And then we get this piecewise linear curve, which is for sufficiently small time steps a good approximation to the ODE solution. So we introduced what we mean by time steps, what we mean by exact solution, discrete solution, and then we generalized Euler's method to a general explicit one-step method by allowing the increment function, which we use. So we always define the next time step yn by adding to the previous time value yn minus 1 h times some increment function. And this increment function can be chosen differently to f, little f, which is the Euler method, and that would lead to a different one-step method. We then we started the analysis of the error and defined what we mean by the global error up to the n time t, capital T, the local error in one time step, and the truncation error, which is the local error divided by the time step size, which is in some sense how well the approximate solution satisfies the PDE, and or approximately the PDE, and then the truncation error for Euler was our first example, calculating truncation error for Euler. Now, as I already highlighted in the first lecture, the error will be contributing in every time step. You get a contribution from the local or the truncation error in that particular time step, but we're starting with the wrong initial guess, so we also get an accumulation of error. And to quantify this this accumulated error is the second part, and to control that we need discrete Grunwald inequality again. Like in the continuous setting, we can say that if we have non-negative sequences now, not functions of time, but this time they're sequences of some index k going to infinity, and bk is a non-decreasing sequence, all of them are non-negative, then if w0 is controlled by b0 and wn is controlled by bn plus this extra sum of ak wk, or from the previous iterates, then in fact wn is controlled by bn times an exponential factor, exponential of this sum of the AKs. Okay, and this is what we're going to use now to prove the main this stability result for one-step methods that I already wrote down last time. So this is now continuing with section 2.2, error analysis, the discrete stability. If the increment function fhk is Lipschitz continuous. So again, we need our Lipschitz continuity in order to get stability, like we did for the continuous setting. But this is, in most cases, capital F. In Euler, for example, capital F is little f. So this is the same as asking for Lipschitz continuity for the continuous problem. So to get existence uniqueness for the continuous problem, we already need Lipschitz continuity. And this capital F is typically some polynomial, simple polynomial of f, or some combination of evaluations of little f at different time steps, or different t's and y's. So in essence, this Lipschitz continuity is fairly unrestrictive. We need it only now at the tk's. We don't need it even in between, so you actually need a bit less. And the Lipschitz constant is again L. Then the theorem states that given this assumption, the one-step method is discretely stable. And what does that mean? If I take two arbitrary sequences yk, zk, starting from y0, z0, and obviously I don't mean them to be completely arbitrary. So for example, I could compare two numerical approximations of the initial value problem with fhk for different initial conditions, u0, v0, or when there is some calculation errors, numerical approximation errors in fhk, or if I want to compare the exact and the approximate solution and take the iterates at the time points tk. But for any of such two sequences, the eta k, which is the truncation error defined by the sequence, is satisfies this inequality, namely that the nth iterate yn zn is controlled by the e to the lt times the initial difference y0 z0 plus these accumulation of truncation errors. And so the sum k equals 1 to n eta ky minus eta kz. So this is kind of an abstract result, but once you put in two sequences coming from two approximations with two different initial conditions, or two approximations, one approximation and the true solution, so yn and un, then this is kind of an error analysis, and this is how we're going to use it. So I'm going to prove this quickly. It's actually just directly follows from the definition of the eta case and Lipschitz continuity, and the assumed Lipschitz continuity. So subtracting the equations, eta k of y, so we had defined that last time. I'll just repeat what we defined it as. It was essentially the discrepancy in the formula, in the one-step formula. So yk minus 1 minus hk fhk tk minus 1 yk minus 1. So if y is in fact the true, actually maybe that's what I'm gonna do, then it becomes less I should never do this in the middle of a lecture. But I want to kind of highlight that this yk does not have to be the exact solution. So let's call it vk. V, we have already used v. What letter did we not use? W we need. Z and X. I don't think we've used X. So what I'm trying to highlight is, I think I'm confusing you now. What I'm trying to highlight is that this xk does not have to be the exact solution. So the point being that we can put in two arbitrary sequences. So the yk we kind of have reserved to be the sequence that's the discrete solution. We've before said that we use yk to denote the discrete solution. Here I'm really making a statement about two sequences xk and zk, and the this truncation error formula. So then eta k of z of the sequence zk is zk minus zk minus 1 minus hk f of hk tk minus 1 zk minus 1. And then exploiting Lipschitz continuity, of the assumed Lipschitz continuity of fhk, it follows that, so subtract the 2, and we get yk minus, xk minus zk in modulus is equal to xk minus 1 minus zk minus 1 plus eta k x minus eta k z plus hk f of hk tk minus 1 xk minus 1 minus hk f hk tk minus 1 zk minus 1. Close the modulus. Let's try and gain a bit of space here. Okay. Now I use, as I said, Lipschitz continuity and triangle inequality, so I can split this modulus up into xk minus 1 minus zk minus 1 plus eta k x minus eta k z in modulus plus Lipschitz constant L hk xk minus 1 minus zk minus 1. Okay. And now I apply this recursively. So I can do that for every k, which means if I substitute here, then my formula for the next one, I get that the nth one, yn minus zn, is less than or equal to xn minus zn. I get xn x0 minus z0, and then I get the sum of all the etas, so sum k equals 1 to n eta k of x minus eta k of z, and then I get the sum of the LHK y xk minus 1 minus zk minus 1, again modulus here, and then I use Grunwald. And let me give a bit of a gap here, because then I can denote all the parts. So the estimate now follows from the discrete Grunwald. That's why I copied it down on the revision part. Inequality. By choosing, so this will be our Wn, so this would be W0, this would be Wk minus 1, then we call the Bn, we call this whole thing. So this whole thing we call B n, and this thing here we call a k minus 1. Okay, so if we use those definitions, let's just write them down, choosing Wn to be simply xn minus zn in modulus, an minus 1 to be lhn, and bn to be x naught minus z naught plus sum k equals 1 to n the truncation errors at the kx minus at the kz in modulus. So just look at it. Okay, so this is precisely the assumption in the Grunwald. So W0 is less than or equal to B0. That's definitely true because we've chosen it equal. So when I put n equals 0, then this is gone. So this is gone, and you simply have that B0 equals W0. So the first inequality holds. And Wn should be less than or equal to Bn, less than or equal to Bn plus the sum of the AKs and the WKs up to n minus 1, and these are basically AK minus 1, WK minus 1 up to n, so that is essentially this sum, because this sum here starts from 1, and we want to start this sum here from 0. Yeah. And then this is Bn. So immediately it follows that Wn is less than or equal to exponential, let's write it fully, xn minus zn, which is equal to Wn is less than or equal to exponential sum k equals 0 to n minus 1 ak bn, and the sum exponential sum of the ak's, the L comes out, so you get exp L, and the sum of the hk is just t, exp lt times bn, and that's just x naught minus z naught plus the sum k equals 1 to n eta k x minus eta k z, and that's precisely what we wanted to prove. It's less than or equal to this. Yeah. Okay, I'll change this x in the notes, this y to an x in the notes. Okay, so we have discrete stability, end of proof. And now we can make a corollary immediately from this result, from the stability result, for specific choices of xk and zk. So the corollary would be, let the one-step method FHK be run in finite precision floating point arithmetic on a computer, yielding a perturbed sequence zk. So zk would be then the zk in the previous result, and let yk be the mathematically correct solution of the one-step method. So the xk would be chosen to be the yk. Then the difference equation 2,1 is fulfilled only up to machine precision, machine accuracy epsilon. So we know that in every step we only have, so we can't represent the exact solution to exactly. So we have the initial condition, or the initial value being only up to machine precision, and each truncation error is exact only up to machine precision. And because yk is the exact formula of the one-step method, we know in that case that eta k, the truncation error formula, is 0. Okay. Then the error between the true solution of the one-step method, so not the exact solution, but the true solution of the one-step method yn, and the computed solution Zn can be bounded by this product, this multiple of this factor times eps. Okay, so we have stability in the sense that we have the eps here and a constant, but as with in linear algebra, the constant explodes with n, with the number of time steps, and it explodes with exponential LT. So you have a rather fast-growing truncation error in this problem. And the proof is application of the previous lemma theorem with, so the proof would be apply theorem 2.6 with xk equals yk and zk equals zk. And then just evaluate the truncation error. Apply these results here. Okay, but more importantly, we can now prove together with consistency results that we had before, we can now phrase the convergence, the global convergence of the one-step methods. Okay, so let's do this slowly. Let the one-step method fk be consistent of order p. So this was what we discussed in the first video this week. Consistency of order p, I didn't revise this, is essentially that I'll write it down again as a revision, that the max of k equals 1 to n of the truncation errors, modulus of the truncation errors, is less than or equal to a constant times the maximum mesh size to the power sorry, to the power p. Okay, so let the one-step method be consistent of order p, and Lipschitz continues in its second argument, so that was the assumption for the stability result for all t. Okay, and furthermore, let the initial condition be the exact initial condition. So the exact initial condition, and as I said, h is the maximum of the time step sizes. Then the global error of the one-step method, so we're really talking now about the global error of the one-step method, converges with order p as h goes to 0, and we have an error bound which is a constant times h to the p, but multiplied with e to the lt. So the constant does grow exponentially in the end time t. So the further along in the future we want to integrate our ODE, the bigger this constant gets, and very fast. Okay, e to the lt. So obviously it's controlled by the Lipschitz constant. If we have a very small Lipschitz constant, this growth would be moderate, but it is still exponential in all cases. Okay, and the constant c, on the other hand, is then independent of the mesh size. So let's just put the things together. So since fhk is consistent of order p, so that was this this result up here. Yeah. It follows that for all k from 1 to n, eta k of u, which is the actual truncation error that we defined, minus eta k of y. So that's if I put the approximate solution in the truncation error formula, which I already said before is 0, because the approximate solution is obviously has no error against the approximate solution, is by this formula here, is the truncation error is the local error divided by hk, so this would be hk tau k of u. So this is not a local error. Let me just be careful that I'm not confusing you, that I'm not getting myself confused with the notation. So eta k, which is the one we have been using all along above. Sorry, that's my mistake. Okay, so this eta k is not the truncation error. I'm very sorry I made this mistake. So this is the in our definition the local error. Yeah. So in this discrete stability result, we have the difference of the local errors coming in, and the local error is hk times the truncation error, and this result means that the local errors are gonna be of a certain precision here. Then we get this result, and now for the consistency of order P, here we have the truncation error, and again the truncation error is tau k is hk is eta k divided by h. So tau k still tau k is eta k, the local error, divided by hk. Okay, so this is what I'm using here, and then I'm using the consistency bound. So I've just said that this is less than or equal to a constant times h to the p times hk. This, by the way, is 2,9. Okay, so now 2,10, and the c is independent of h. It's the constant from the consistency bound. Now, since f of hk was Lipschitz, in y, in the second argument, we can apply the discrete stability result. We can apply theorem 2.2.6, which I proved at the start of today's video, and use the bound in 210 to obtain. So we now know that we have a bound on these eta k's, which is CHP HK. So now using the inequality from the stability result, which was simply UN minus YN, so can apply, can apply theorem 226 with xk being uk, the exact solution, and xk being yk doesn't really matter in which order I pick it, and zk being uk, and use 210, we obtain that un minus yn in modulus is less than or equal to e to the lt. That was the constant in that bound from the stability result, times sum k equals 1 to n modulus local error at the ku minus local error at the ky, which was 0, and now used to 10, then this is less than or equal to e to the lt. C times HP we can pull out because it doesn't depend on K, and I'm ending up with some K equals 1 to N HK, and that's T again. So this one is T. So we get constant C times T times E to the LT times H to the P. And we have essentially got our bound. So this T can get absorbed into the C here. Okay. But importance being that it's exponential I'm gonna write it explicitly in the lecture notes. I'm gonna correct it. But obviously the more important one is the exponential one, which grows much faster. Okay. A corollary is that corollary 2.2.9 is simply that if f is actually C1 in a compact set D around the graph of the solution, graph of U, over the whole interval 0 to t on which we want to integrate, then the convergence order of the global error in the Euler method is 1. So we can immediately apply this result above to Euler method, where f of hk is just f, little f, and deduce that Euler's method is order 1 because we've already proved that it has consistency order 1, and therefore it has global error order 1. And important, the way we prove this, and this is a general approach in numerical analysis, not just in ODE numerics. This is essentially how most numerical analysis works. We take a consistency result and a stability result and combine them and obtain global convergence. So I gave this even a number so I can refer to it later. So essentially the way you're proving convergence and convergence rates of numerical methods is typically that you prove consistency and then stability, and which then automatically gives you convergence. Okay, let's go to the next class, or a more specific class of FHKs. So this is a subclass of explicit one-step methods called Runge-Kutta methods. So, and they are getting designed, and we're designing them on the basis of the Volterra integral equation. So since the initial value problem is equivalent to the Volterra integral equation 112, we can consider the numerical solution of the quadrature problem as a quadrature problem. And that's one way of designing clever or other higher order one-step methods or increment functions that lead to higher order one-step methods. However, if you look at the integral equation, maybe have a stop of the video and look back, or open your notes and look at it, the difficulty is that the integrand in this Volterra integral equation depends on the solution. So if you haven't got the solution, you can't put it into the integrand and use a quadrature rule. So we need to somehow interpolate or extrapolate the solution to evaluate this integrand. So it depends on the solution on which is unknown. Oops. So it will need to be approximated on each interval from values at earlier times. And this leads to a class of explicit methods of one-step methods for initial value problems called Runge-Kutta methods. And again, we'll, as I said last lecture, present the formula only for the first time step, for step from T0 to T1, and then it's implicitly also defined for step K by simply replacing. So for step K, simply replace K minus 1, 0 goes to K minus 1. And 1 goes to K in all variables. The coefficients remain fixed. Okay, so here is here are explicit Runge-Kutta methods, which are one-step methods, special one-step methods, and they use S evaluations of the function f. So we've seen already the Euler equation simply evaluates f at the previous time step, so it uses one evaluation. So Euler is a one-stage Runge-Kutta method, and in general we can have S stages. So these intermediate evaluations of f are called stages of the Runge-Kutta method. And well, the formula looks quite straightforward, but you simply evaluate f at the following time points. You take constant ci, so the important bit is there's a constant ci in there, and it's it's usually Ci will be typically less than 1 or less than equal to 1. So you basically take a sub-step. You don't quite add h, the full step size, but you add some fraction of the step size, and you take the previous gi and you evaluate the function itself as an extrapolation of previous calculations. So the 0th one, so here is the function values that you're putting in. So the previous one, the 0th one would just be y naught. If you've got g naught, then it's just y naught. But if you are at g1, g2, etc., you take previous function values and you take a linear combination of those with some factors aij. So again, the aij's will typically be less than or equal to 1. So you take a linear combination of function evaluations, and that goes then, so this g then goes in here, yeah, and then you do that s times. Okay, so this is a loop here, and at the end you end up getting s such values ki. Okay, so you get s function evaluations at s intermediate points with s intermediate second arguments of the solution u. Okay, so the k's are evaluations of f at intermediate points, and the g's are intermediate values of the u. So these are kind of approximating. These are kind of approximating u at some point, and then these are approximating f at some point. And at the end, you plug it all together and you end up getting a final formula, which is given here, which is that the next iterate in your numerical method, or the answer of your one-step method, is simply y naught plus a linear combination of these ki's, and again the bi's are these factors with which you doing the linear combination. And the increment function can then, from this formula, simply turns out to be given as is here. Okay, so it's a linear combination of s evaluations at some intermediate points of the right-hand side function f. The values of where we're evaluating in terms of t. So the values t naught plus CIH are the quadrature points on the interval t naught t1, and the GI's are the approximations to the solution at t naught CIH. Okay, and you do some extrapolation, as I said, in order to get those values, because we're not explicitly wanting to compute u at an intermediate point. We're just using extrapolation, using some function evaluations. And since this method uses s intermediate approximations, I should have highlighted this. I make this bold in the lecture notes. This is an S stage. It's called an S stage method. So these S function evaluations are the S stages of the method. Okay, so in typical remark 2.3.3. So in typical implementations, one doesn't actually store the values, the intermediate values. GI are not stored, because we can just increment this step by step here. So this function here can be incremented step by step. You just say y1 is y0, and then in the next iteration you add h times bi ki, h times b1 k1, then you add h times b2 k2, and so on, and at the end you have the formula. The intermediate values that you're computing in here can just be discarded after you've used them. So they're not stored, but they're useful to highlight highlighting the structure of the method. So there's another way of formulating this in a more compact way, which we're going to use quite a bit, and which is basically giving you a way of handling this more. This looks fairly complex here, and you can make many mistakes. So Butcher in New Zealand came up with a way of writing all Runge-Kutta methods in the form of a tableau, in the form of a table. And it basically lists the coefficients of the equations in 212 in a matrix form. So I highlighted already the C coefficients, the Aij coefficients, and the Bj coefficients. Essentially, you put the C coefficients on this column here in this tableau. You put the B coefficients at this row at the bottom, and you put the matrix coefficients A, Ij into this middle bit here. And because we want to work forward, we kind of want to do a forward substitution. The first one only depends on the previous. So the first thing here, so in this sum here, the first GI only depends on the ki minus 1s, at 1 to I minus 1. So these Aij's are 0 for all j bigger than I, bigger than or equal to I. And that's why this is a lower triangular matrix here. Okay? And the first row in the tableau, where we've not written anything in, is simply should be read as, because there's an empty sum, remember, I'll highlight it in a minute, should be read such that C1 is 0, G1 is Y0, and K1 is computed directly from F T0 Y0. So K1 is essentially the Euler approximation, because essentially you're taking C0 is not, so we're actually evaluating at T0 here. So C0 is not, so we're evaluating at T0, and as I said, G0 is Y0, and so essentially K0 is simply F of T0 G0 Y0. So the first K that we're getting, K1, is simply K0 is simply F of T0 G0. So we're not actually computing anything, because here the sum only starts at 1. Okay. It's just so that for the next iteration you know what you have to stick in here. So there's no actual calculation on the zeros level, but you need to know what value you stick in. And the method is explicit, This will become a bit more apparent once we also have defined implicit methods later on, but I say it already here, so don't take too much note of this at the moment, but it's explicit since the computation of ki of each stage only involves coefficients with index less than I, and therefore only already computed objects. So there's no nonlinear solve needed. We don't need to solve some equation system. We can just calculate ki from the previous values. And the row below the line, so this is the bi's, is the short form of equation 212c. Let me just show you that. So the bi's are basically what enters into this final formula, namely here that the next iterate y1 is computed as y0 plus h times some bi ki. And so the bi's describe how you're adding the computed ki values. So the bi's here describe that in the tableau. And in fact, it basically thus lists the quadrature weights in essence. In the increment function. FHK. Okay. So considering now a little bit more simplification, considering, as the notation already suggests, the coefficients aij as entries of a matrix, as entries of a square S cross S matrix A, hence the notation aij, we see that A is strictly lower triangular. I already highlighted that. So there's no entries on the diagonal, or the entries on the diagonal are 0, and the entries above the diagonal are 0. And this is the defining feature of explicit. Runge-Kutta methods. So this makes a Runge-Kutta method explicit. We will later see Runge-Kutta methods with full or fuller A, and those will be called implicit Runge-Kutta methods. And they're called implicit because, as I already highlighted above, the computation of the stage values involves also the value at the current or possibly even future stages. So here, if I actually don't restrict this sum here to a sum from j equals 1 to I minus 1, but make this a sum up to n, so the coefficients here are non-zero also above the diagonal, then I can't just simply compute each individual gi and then calculate the next. I have to solve them all together. I have to solve one big system of equations. And this system of equation involves the nonlinear function f here. So essentially we have a nonlinear system to solve. But that's not impossible, and that is an important class of methods as well. But they are called implicit Runge-Kutta methods, and we'll discuss them later. And the other thing we do is, for simplicity, we will also write the whole vector of quadrature weights as a vector. So we just make B1 to be S, the vector B, and we make C, the vector C not C2 to CS, such that the butcher tableau can be further simplified to simply writing C A B transposed. Okay, so this is now a very, very compact way of writing one-step methods, in particular Runge-Kutta one-step methods, and we'll look at our first example again, the one we have already looked at several times, the Euler method. Has butcher tableau, very trivial, 0, 1. So essentially B is the vector with one entry, sorry, C is the vector with one entry, 0, B is the vector with one entry, 1, and A is the matrix, which is essentially it's just a zero scalar matrix. And this leads to the already known formula. If we look at our Runge-Kutta formula, I essentially end up getting y naught plus h times sum bi f of t naught c I h g I, but if the only entry we have is the case c1 equals naught, g naught equals y naught, then I'm just getting 1 times f of t naught h naught, f of t naught y naught. And you can also read off certain things from the values. So the values b1 equals 1 and c1 equals naught indicate that this is in fact related to the quadrature rule I told you before. The Runge-Kutta methods are based on quadrature rules. So this is related to the quadrature rule with a single quadrature point at the left end of the interval and there's a quadrature rule. This rectangle rule, as it's called, is exact only for constant polynomials. So in the numeric 0, we call this the Genauigkeitsgrad. So it has Genauigkeitsgrad 0, and therefore quadrature error is always d plus 1, the degree of accuracy plus 1, and so it is of order 1. Okay, so we've already established this, that the Euler method is of order 1, but it relates also to the quadrature rule that the Runge-Kutta method is based on, which is also of order 1. So now let's try and come up with methods that are of order 2. So, and we are inspiring ourselves by using quadrature rules that are order 2. And we know, for example, the trapezium rule or the midpoint rule are two quadrature rules that are order 2. And so we're going to use those first. Let's do it in order. So the modified Euler method is a variant of Euler's method of the following form. So you take, in the first stage, we always take just f of t naught y naught. We already said that. That is this simple row 0 empty. So all explicit Runge-Kutta methods have k1 equals f of t naught y naught. And then, instead of evaluating immediately y1 as y naught plus h1 k1, we do an intermediate stage. And the intermediate stage is based on the midpoint rule. So this is based on the midpoint quadrature rule, or the 1-point Gauss rule. And so we're evaluating at the midpoint the quadrature formula. And so we're basically evaluating t naught plus a half h1, y naught plus a half h1 k1, and use that as k2. Because then essentially the quadrature rule for the Volterra integral equation essentially replaces the integral with a midpoint evaluation, and the midpoint evaluation is essentially saying we're not taking the left endpoint. So the important bit is we have a 0 here, so we're not taking the left endpoint. We're only taking quadrature weight 1 on the midpoint, which is exactly the midpoint rule. So we're only taking k2 into consideration, and the length of the interval is h1. So the weight is the quadrature weight is 1 times the interval length, which is h1. So this is based on the midpoint rule, and then the Hoehn method of order 2 is based on the trapezium rule, on trapezoidal rule. So what do we do here? We take, again, as I said, always k1 is f of t naught y naught, and now we do an extrapolation step to the end point. So we go to t naught plus h1, and we add to y0h1k1. So our two quadrature points are not the left endpoint and the right endpoint. And we're taking, in the final quadrature rule, we're taking both of them into account with a half, weight a half. So we have a half from the left, a half from the right, and we take a half the value of the integrand at the left plus a half the integrand on the right. And that's basically the trapezium rule. So let me just write this explicitly in remark 2.3.8. So the modified Euler method uses one quadrature node at t0 plus h half, which is t0 plus t1 over 2, and an approximation. So you don't know the solution, but we use an approximation of f of t0 plus h half and u of t0 plus h half in the increment function. So this corresponds, I've already said it, to the midpoint quadrature rule, or the Gauss quadrature rule of order 1, of order the 1-point Gauss quadrature rule. To the midpoint, it is of order 2, of course, sorry, quadrature rule. The Hoyne method, I'm not going to write all the details out, of order 2 is based on the trapezoidal rule. So both quadrature rules are of order 2. And so are the Runge-Kutta methods. And they both were discussed in the original Runge article. From 1895, so quite a while ago. Okay, so let's write this down as a lemma and prove it. For f sufficiently smooth, there's another thing that needs to be. So if f is sufficiently smooth, the Hoyne method of order 2 and the modified Euler method have both consistency order 2. And in the following, I will often do this. I will not explicitly write down how many derivatives are necessary. We're always just gonna assume that all the derivatives that appear in the proof are bounded, and we just simply write f is sufficiently smooth. Okay, it should always be clear from the context what that means for the particular method. Okay, so let's prove this. So we're using again Taylor expansion of y1 and the exact solution y1 and the discrete solution u1 and the exact solution u1 and the approximate solution y1 around t0 and initial condition y0 equals u0. So we're fixing the there's no error for this consistency proof in the initial condition. We are setting both initial conditions the same, and we use Taylor expansion to compare u1 and y1. And without loss of generality, I've said that already many times, we set t0 to be 0. So let's only consider the case d equals 1 at first, because that simplifies notation tremendously. And we also use the abbreviations that f sub t, by f sub t I mean the derivative with respect to t of f at t u0, so the first with respect to the first argument, and f sub y is the derivative with respect to the second argument. So dy f t0 u0. So it's the evaluation of the derivative at the initial point t0 y u0 of the first derivative with respect to t and of the first derivative with respect to y. And we're also replacing u primed of t0 immediately as we did for Euler by f of t0 y0, and I abbreviate that as f. Then we get the following. So u1 is u of h, and u of h can be expanded in a Taylor series around u0 by adding h times f of t0 u0 plus h squared over 2. And now we have to do the time derivative, but because both the arguments depend on time, we end up getting the product rule and the chain rule, so we get ft plus fyf. Okay, maybe for this one first step, I'll write it out, and then I'll just never explicitly do this anymore. So if I take the derivative of f with respect to t, then I essentially get d by dt of f of t and y plus d by dy of f t, sorry, u of t, u of t plus d by dy of f t u of t times d by dt u of t, all evaluated at t u at t equals t naught, sorry. Okay, plus the next one, I'm not writing the next one out in full, so the next one would be h cubed over 6, two derivatives with respect to time at time t naught, plus 2 times f of ty f plus f two derivatives with respect to y times f squared plus fy ft plus fy squared f plus, and then h to the fourth divided by 24 times dot 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 plus dot dot dot. Okay, so this is 214. So as I said, in the first one I did it explicitly, and just to compare notation again, so we abbreviate by these derivatives here. So here we have this time derivative at t equals t naught, and so this one would simply become f sub t in our abbreviation, and then in the other part we have d by d df by dy at t naught u naught times d by dt of u. So here's the third one we abbreviated, so u prime is f. So this would be our f sub y, and this would be our f. Okay, and the same holds for the second derivatives, which I'm using here in this second formula. So this is very synonymous for all the analyses that we're going to do in this course. We're going to do a lot of these manipulations of Taylor series expansions. So, and in particular, we'll always have these f's that depend on two arguments, on t and u of t. And therefore, you'll always get the product and the chain rule appearing immediately. And even in this third derivative here, already we end up with 5 terms, sorry. Okay. For the discrete solution, of the, so this is the, we're now gonna look at the two methods. So in particular, we start with the modified Euler. In fact, I'm not gonna actually explicitly do the Hoyne. I'm only gonna explicitly do the modified Euler. I leave the Hoyne as an exercise. Again, Taylor expanding f. Now we're expanding f around. So because y is just a discrete solution, we can't do any Taylor expansion, but we can expand f around t naught u naught, and so that leads to, okay, y1 is equal to y naught plus, so first we write down modified Euler. Modified Euler is f times t naught plus h half u naught plus h half f of t naught u naught. Okay, and so now I can substitute. I can expand f in a Taylor series, because this is essentially the, okay, let's do it in two steps. So we do f of t naught plus h half u naught plus h half f of t naught u naught, and that obviously is equal to f of t naught u naught plus h, if we've only taken a half step here, so h half times f of f sub t plus fyf. Why is that? We've basically again taken the derivative of f with respect to time t, and that ends up with this formula as before. We didn't really do anything different here. And h squared over h squared over 4, sorry, now I got it. So we have h squared over 8, sorry, h squared over 8 because we're taking a half time step. Yeah, sorry, h squared over 8 because we have h squared over 4 halves. Okay, remember in the Taylor expansion the second term has a half in it. Yeah, but since we're taking h over 2 as our time step because we're only going half a time step here, we end up getting h squared over 8, and then now we're getting ftt. So we just have to do the second derivative of this thing now. So this is ftt plus 2 ftyf plus, I need a bit of more space here. Let me give myself a little bit more space. So I write a little bit smaller. F sub yf plus h squared 8 ftt plus 2 times fty with f plus fyy times f squared plus, and then the next step would be h cubed to the 8 and 6 is 48, etc., etc. Yeah. Now I have expanded f. I can stick that into my formula for the modified Euler. So y1 modified Euler says y1 is u naught plus h times f at what I've had here. U naught plus h half f times t naught u naught. And so as in essence I end up getting f u naught plus h times f plus h squared half times ft plus fy f plus h squared 8 times ftt plus 2 times fty f plus fyy f squared plus da da da. Okay, so I've simply substituted this thing in here. I've simply substituted this thing in here, this expansion in here. Okay, so now this expansion of y1 and this expansion of u1 that I have, so I have here an expansion of u1 and here I have an expansion of y1, I can subtract them. So thus the truncation error tau 1, which is h 1 over h times u1 minus y1, is, I can actually explicitly in the lecture notes, it's written very crudely. I essentially end up getting that the u0 f cancels. So here we see immediately that u0 cancels against u0, hf cancels against hf, h squared cancels against h squared half, and all we're left with is this term here versus this term here. Oh, there's a cube. I forgot to put a cube here. Okay, so these h cubed things appear, and what you end up with is so this h squared times, okay, what do we get? We get from this one, we get, let me write it down below. Let's write it as constant. Where c is in fact, so taking those two together, so we have here 1/6 ft2 fty f fyy f squared fyft and fy squared f minus 1/8, and now this guy's here, ftt plus 2 ftyf plus fyy squared, and that's the constant. So in general, this thing here says that the method is, of course, of order. So tau 1 is h squared times this constant that I can write down explicitly, plus something that's order h cubed. So in total, this means that the truncation error is of order h squared, is of consistency order a. P. Thus, the modified Euler method has consistency order 2. And the proof for the Hoyne method, as I said, is identical, and I leave it as an exercise. Okay, so that was the case d equals 1. Now for d greater than 1, the derivatives with respect to y are no longer scalars. They're no longer just numbers, but tensors of increasing rank, or equivalently multilinear operators. So you really need to be precise. I'm I'm only going to highlight this. We're not going to do this over and over again, but when you're looking at this formula here, for example, then you really need to think of this thing here being vectors. So this is a vector and this is a vector. So this becomes basically a vector product. So you shouldn't really think of this product here as that you can divide through or something like that. This is a scalar product. And equally here, this is a matrix. This is a matrix. Sorry, this is a vector. This is a, because it's the t derivative. This is a vector times a vector. This is a matrix times a vector. Okay. This is a and so on. So you need to really be careful that this is a matrix times a vector. This is a matrix times a this needs to really be written in a different way, because you end up getting you have to contract this to a scalar again, and these are basically a vector. This is a matrix times a vector, and this is also a matrix times a matrix times a vector. Okay, so it always needs to produce a vector. So this is a vector. This is a matrix times vector. Sorry, this is always matrix times vector. This is an order 3 tensor times a vector times a vector. This is a matrix times a vector. This is a matrix times a matrix times a vector. Okay, so you need to really be careful when you write these derivatives out. So thus, to be precise, in d dimensions, as I said, dy f of t naught y naught is a d cross d matrix that is applied, multiplied with to the vector f of t naught y naught, and we should write more carefully the f y of f, really, because it's a linear operator. So the linear operator defined by the derivative with respect to y of f. So if you write it as linear operators, then the notation becomes very clean. And so you get a matrix dy f t naught y naught times a vector f of t naught y naught. U naught, well, yeah, y naught is the same. Similarly, the yf at t naught y naught or u naught is a d cross d cross d rank 3 tensor, or more similar as simply a bilinear operator. So it has two arguments, a bilinear operator, and to stress this, we write f y of f and f. So it's an operator of two arguments instead of as we did above, fyy f squared. But we will not dwell on this issue in this course because it becomes very quickly very tedious. I just want you to be aware that if you go to d dimensions with these ODE systems, you have to be careful. You have to use vector calculus and not scalar calculus. So the Taylor, please do recall what Taylor series expansion in multiple dimensions does in order to not make any mistakes in your Taylor expansions. Okay, so I just realized that I've run out of time. I was gonna present a three-stage Runge-Kutta method that's got a higher order, but I will come back to that on in next week. So the next thing we'll see is now a three-stage Runge-Kutta method with, again, the first stage being f t naught y naught, and then I have two more intermediate stages and a quadrature rule at the end, which, as the alert by you already notice, looks very much like the Simpsons rule. And so this is basically going to be a method that is based on Simpson's rule and has even higher order. Okay, so that's it for now. See you next week.